You're putting it in the chat, right? Okay, yeah, just put it in the chat. So I'm ready for that. Okay, well, it doesn't look like anyone else is coming. So I will just begin. I'm recording right now. So we left off with this discussion. You remember this problem? Last class? Okay, so the final answer was 9604. And I left you to think about why I chose E. So why did I choose E? Okay, so wait, let's go through. I put two problems up. One was this one with the options. Clearly 10,000 is the answer if you choose, if the question is worded like this. But then I changed D to say 9600. So now it looks closer. But I asked you why I still stick with 10,000. What is the answer? Why do I continue with 10,000? Not D. So we're trying to be precise. We want to be within 2 percentage points width. So we want it to be tight. If we have, and remembering the formula for margin, remember this formula comes from the formula for margin. What is the margin of error? Margin is equal to C star, right? So that's the times the standard deviation like that. So the N is here. I should make that line a little straighter. So the N is here. The larger the N, what happens to the margin? What is the effect as N goes large? If this goes higher and you're dividing by a number that's larger and larger and larger, and it's an integer, then this one goes down, right? So we don't want the margin to be smaller. We want it to be, sorry, I want the larger margin. We want the, sorry, let's do that again. If the margin goes smaller, then we are within the width, right? We're going to stay within the estimate. We want to have a width that's within 2 percentage points, or a margin that is 1%. So the larger N will make sure that happens. If we go with a smaller N, so we go down instead to 9600, if this is smaller, what happens to M? It goes bigger. So it exceeds the margin that is established, pre-established, or specified at the outset. Okay, so that's why. So we jump all the way to 10,000. Don't stick at the number that's closer. So that's the rule for sample size estimation. You need to remember that because you're going to have some options like that. So as I said, this was the margin of error using p hat from the sample. And we solve for the sample size estimate by isolating N and taking these as given, recognizing the relationship between them and these other variables. As a researcher, you can specify the confidence interval level you want. You can specify the level of the margin or the amount of the size of the margin. And P is not exactly chosen, except that if you don't have a given value or the God-given P known, or you don't have a result from a previous sample that you trust, you have to stick with P star equals 0.5. Okay, so the researcher, the student conducting the study will pick what they want these to be along some standard. What did I tell you that usually Z star is, what's the confidence interval frequently used in statistics? Right, Alejandro, 95%. So with 95%, what is the Z star? So for 95%, the Z star, actually, I can get it from here. Oh no, I can't get it here. It's in here. All the tables that you need are in module 9. So for 95%, it's 1.96. Okay, so you get used to that because that's usually what we use. If I don't specify what you need to use, you use this one for Z star. If I do specify, you look for it on this table. If it's not on this table, what do you do? What do you do if it's not on this table? If I ask you for 93% confidence interval, you need to go back to the Z scores and find it here, right? You have to basically answer the question of what is the Z score that gives you, yeah, I'm not going to draw it there. So what, oh, that doesn't look like 93. So you want to find the limits the old-fashioned way. From the beginning of the course, we learned how to do this, right? How do we find this? Okay, so if it's not on the list, that's what you do. The list is just a more, a list of the more popular confidence levels. Z star for the most common. Okay, so you have to calculate manually. That's right. Okay, so back to where we were. No, the problem is in this one here. Okay, the problem is here. Oh, I keep opening the wrong one. Okay. So what we have next is one more time. What we have remaining is in this row discussing inference on a population proportion P. What we have remaining is to discuss this column. Now, if you've gone ahead and you've studied on your own, that's what I've hoped, you know what this column references. We're going to learn about, we're going to review what's called tests of hypothesis. Hypotheses. Tests of hypotheses. or significance testing. Okay, what are we talking about? First, I want you to notice the whole row concerns inference on a population proportion, P unknown. Notice that in each formula, there's no P. There's P hat in this one. There's P star in this one. There's P hat and P zero, P naught or P zero, sub-zero in this one. But there's no P. Why is there no P? Because P is unknown. We don't know P. All right. So what am I doing here? What looks familiar here? What do you recognize in this formula here? What do you recognize? What do you recognize? Well, I recognize Z. What's Z? What does Z represent? You guys are delaying the class. You're not aware? You're waiting for me to tell you? You don't know? What's Z? Z is a standard normal with a mean of 0 and a standard deviation of 1. So how do I get the standard normal? I have to standardize. I have to standardize a value by subtracting the value by the mean, its mean and its standard deviation. So if X is given as normal with a mean of mu and a standard deviation sigma, the relationship between them is a standardized score. Okay, so I'm just going to talk because you guys are in your bubbles, thinking bubbles, I guess. So I'm just going to rattle this off. So this is a standardized value taking the X, that's normal. So what's our X in this case? What's our variable of interest? It should be P hat if you're going to follow this. The mean of P hat should be P0, and the standard deviation of P hat should be this thing here. Where is that coming from? Where am I deriving that from? I'm taking it from the theory above. Here, where it tells me that P hat which is x divided by n, where x, remember, x was binomial. So this is a different x. This is not a normal x, okay? Even though I wrote it down there. So I'm trying to remind you where we started back in before the first test. But if x is binomial and we convert it from the number of successes to the proportion of successes, it has a mean of p and a standard deviation of p, 1 minus p over n square root. And if it satisfies certain conditions, x becomes approximately normal. So this is what I'm using. I'm using number 2. But I don't have p. So what do I do if I don't have p? This is really important. So you're not just making calculations and not knowing what you're doing, because you can confuse the p hat, the p star, and the p very easily. Why am I don't have p, so what do I do instead? So this is telling me if I have x that's binomial with n and p, and n has a certain criteria that's established here and here, then x is approximately normal with a mean of, sorry, I have to use p hat. I'm doing the wrong one. So if this is true, then p hat x over n is approximately normal with a mean of p and a standard deviation p 1 minus p over n square root. So that's what this number 2 says. But in number 4, I don't have p. So what do I do instead? What I'm doing is saying that p hat is approximately normal with a mean of p0 and a standard deviation p0, 1 minus p0 over n square root. What is p0? P0 is a hypothesized value for p. So what you're doing is you're guessing, educated guessing what p could be and calling it p0. When you do that, you can activate number 2, formula number 2. So I put p0 in here, I standardize, and then I verify if it makes sense. That's what I'm going to do. All right, so I'm going to look at a problem now so we can do this together. But that's what this comes from. This is just a standardized score like we did before. So we've used that before. But now I'm going to use it for this normal distribution, x over n, where x was binomial. I'm going to do this for p hat, where p hat's mean was p0, and it has a standard deviation like this. Okay, so this is known as the null hypothesis. Okay, this is what I'm guessing p0 is. I put my, I put my neck out and I guess that it's p0, and then I check if it makes sense, given that p hat should be normally distributed. That's what I do. And we know a lot about the normal distribution. We know that outliers occur 0.3% of the time. We're going to use that fact to test if what we have as a result of using p0 as the mean, if what we have is within 3 standard deviations or so from the mean. But I'm going to be more precise than saying it like that. All right. So let's go look at a problem. And if you've checked the notes already, then you would have seen I did this before. So the problem I'm going to look at, oh, that's not it. It's going to be over in this set here, the tables. Let me stop for a second here. Okay, I found it. All right, I'm going to share. There's the question. All right, so this should be review if you watched the video already, but I'm going to do it anyway because it's an introduction to the topic. Okay, so here's the problem. A random sample of 900 individuals has been selected from a large population. If you remember back to the formula sheet, we need the population to be large, not the sample, the population that it's drawn from. It was found that 180 are regular users of vitamins. Test a suspicion that less than 25% of people use vitamins. Oh, sorry. All right, so how we do this, I explained that I'm going to do this in 5 steps, known as the HAP-C steps. Not happy, but HAP-C, because you arrive at a conclusion. That's the C. So for the H, the hypothesis, or the hypotheses, I have to set up the problem. And the problem is always set up like this, okay? And I have questions if you've started the review or if you've done the review, where I test your understanding of this statement, okay? This is really important because it sets up this problem. And whatever number you put here, this is the null hypothesis, you're also going to put here. Okay? It translates down to here. The sign that you put here has to be different from equals. The options are that you're going to test against, this is the alternative hypothesis. If the null is found to be false, then the alternative, it suggests that their alternative is true. So those are the options for that. So every problem for hypothesis testing that we're going to do looks like this. Some people have constructed it looking different, but this is the way I do it. And it's safe. You can trust this method. So first we begin with the null hypothesis. The null hypothesis, null is like nothing, nada. That's how you think about it. Nada what am I saying? I'm saying that there is nothing new. It's just the status quo. What we always believe to be true goes here. So this is really important in any kind of research that you do, that you establish the what is believed to be true at the outset. And then you try and disprove or falsify your hypothesis. That's the approach of the scientific method. So we try, we state a hypothesis, and in this case, we're going to get the number from the problem there, and we're going to translate it down here. Well, we're going to write it down here as well. And what is this down here? This is called the alternative hypothesis. In other words, what we believe to be true in the event of rejecting H naught, the null hypothesis. Okay, so if we find evidence against the null hypothesis, then we say the alternative is true. So this has to be mutually exclusive, really. All right. It cannot be, it cannot include equals. It's either greater, less, or not equals. All right, so let's read the problem. It's a very short problem, and there's just a few numbers here. So let's go through and see what the numbers are. Our random sample of n, what is that? What do we call that? The random sample of 900 individuals is n. Has been selected from a large population. It was found that 180 are regular users of vitamins. What does 180 represent? One 180 is not P. What does 180 represent? So I'm going to look at 900 individuals and I'm going to ask them, do you use vitamins regularly? And then I'm going to count how many use vitamins. That's my successes, right? 180 represents what symbol? Ah, good. X, the number of successes, or the number of people who use vitamins. Great. Okay, so we have X and we have N. Now what do we do? What can we do with that information? That's our sample result. Excellent, Jennifer. So P hat, we calculate P hat. P hat is a statistic. X is a statistics, but we're going to use P hat because we're talking about the proportion in this. All right, that's how I know. So X over N. X is 180. N is 900. So what do you get when you make that calculation? P hat is known as the sample proportion. I observe that, but I don't know the true proportion. That's the story here. 0.2, excellent. All right, so now we have talked about this number. We put them together to create this number, P hat. So that's a statistic from the sample. And now there's only one other number here. Tell me what do I say about that? What I got in the sample and what I'm staring at, that other number. There's only one other number. I do not put this number, 0.2, that you compute here. That's not the goal, okay? The goal is to identify the status quo belief. What is it that we believe to be true? And we have a suspicion to test. So from this very simple example, we're going to deduce that, and simple in the sense there's only 3 lines here, 2.5 lines of code. The status quo is going to be 25%. Damaris is right. Yes. So we're going to take 25% because we don't have a choice. Always, this has to be equals. This is what reduces the options for me and avoids confusion. We're going to fix what P is given the status quo. Now, the way this is written, I can't put less than 0.25 because that's what I'm going to test against, right? The status quo. So the status quo belief is 0.25. Actually, I'll use a different color. That 0.25 goes here. And I told you, whatever number I put here, I have to put here. So I put that there. And then the last thing I have to do is find what the sign is here. What sign do I put here? What should be the alternative if this is not true? Which symbol do I pick for this problem? Very good. No, that's Eliximar, Brian. Very good. Okay, so you see, it that's all I'm down to, less than 25%. So that's going to be, I'm going to use a red, less than. All right. So that's it. So that's what we're going to test. This one always has to be equal, whether it's a proportion, a test of means, a test of variance, which we're not going to do in this class, but this is always equals here. All right, so before we continue, let's stare at this a moment. The statistic that we computed was 20% or 0.2. Let me write it as a percent so it looks more similar to the status quo. So we got 20%, but the status quo belief is that it's 25%. Do you think our statistic supports the hypothesis or will falsify the hypothesis? Will reject the hypothesis? What do you think? Just looking at the numbers, we haven't done any calculations beyond this yet. What do you think? What's your feeling? Are we going to reject 25%? Because we got 20% in the as a statistic of the sample. What do you think? So put in the chat, reject the null, reject the status quo if you think we're going to reject. It's 20% smaller. So if somebody says to you that you have to pay 20% taxes, but then you find out that you have to pay 25% taxes, are you mad? Okay. Those are not the same number, right? Those are not the same number. That's how you should feel. The 20%, it's not the same number. So that we have some evidence to reject. Exactly. That's how you have to think. It's a different thing. So what's going to determine, why do I have to do the next 4 steps? I have to do the next 4 steps because from every data set, from every sample, there's a different idea of what is big or a small difference. And that is in the standard deviation. We really need to get the standard deviation and standardize this number to see if it's too many standard deviations away. We learned that already, but that's how we're going to apply it. Okay, because our feeling is like, no, I think 25% is a lot, and I only want to pay 28%. But let's see if it's really different in statistical terms. It's going to depend on the standard deviation. So let's do that. Next step. Next step. Very good. You guys are following me. So A is assume. What do we assume? We can't do anything unless we make this assumption. Sorry. I'm flipping my... I'm moving around too much. Okay, hopefully I can stay in this position. Okay, assume H naught is true. We can't do anything unless we assume that. So if that's true, then P hat is approximately normal with a mean of, go back to number 2 on the formula sheet, with a mean of P and a standard deviation P 1 minus P over N square root. But I don't know P. I'm going to hypothesize that it's P0, you see. So this is the powerful thing that I do. I assume. I make the assumption, and then I check if it's a good one, if it's accurate, by using the normal pattern of the distribution. Okay, so I assume H naught is true. So this is from number 2 and number 4 of the formula sheet, right? Because I don't have P, so I'm going to use P0 instead. And let's calculate then. So what is P0? P0 is in this column here. Okay, that's what's there in that column. So P0 is 0.25. So then the standard deviation is going to be 0.25 times 0.75 divided by N. What's N again? 900 square root. So get this number. This is the mean of P hat. This is the standard deviation. And we're going to call it the standard, well, we can call it the standard error in general because It is a standard deviation if I believe that to be true, but we'll just call it the standard error because that's the word we use when we substitute in here anything but P, okay? The real one. We don't know the real one. So do this calculation on your calculator. Don't forget the square root. 0.25 times 0.75 divided by 900 equals, and then square root. So I get 0.0144. All right, so we've done that. So we found the mean is 0.25, and we could write it again if that makes you feel better. We can write it again. Okay, so the standard deviation is very small. You see that? 0.0144 is pretty small. So I think you're right that we will reject because being 0.05%, sorry, 0.5% difference between the statistic that we calculated and the hypothesized value will be many standard deviations away. I'll say that we have something very odd. So let's continue here. So assume H naught is true. The next step is to assess A, or assess the evidence. Assess the evidence. The evidence is P hat is equal to 0.2. Assessing it means find Z. Find how many, the number of standard deviations. Okay, let's just do it like how far away is P hat from P0. Okay, that's what we're figuring out in terms of standard deviations, because that's what we learn in statistics is the regular expected, spread of this distribution because it's normal. So we're going to use standard deviation. So we're going to take the value P hat, we're going to minus its mean, and we're going to divide by the standard deviation or standard error, we'll call it. So P hat was 0.2, the mean was 0.25, and the standard deviation was 0.0144. So what do you get when you put that together? .2 minus 0.25 equals divided by 0.0144 is negative 3.47. Aha. How do you conclude this? Is P hat that we got, is it an outlier? It's 3.5 standard deviations away. So we're not finished yet. We still have 2 more steps, but we're going to say looks like P hat is too far away. 3.47 standard deviations or standard errors below the mean. So we pretty much have shown that it's far away, but we're going to write it in 2 different steps. We're going to do 2 more steps here, but we pretty much have the answer. It's 3.5 standard deviations away. That's far away that we're going to reject. It's rejectable for that reason. So different. We have evidence to reject. Those are that's the terminology that I use regarding that. So let's do the last 2 steps to formalize our findings. Okay, we're going to calculate what's called for P, a p-value. What is a p-value? A p-value, you can think about it in words or you can think about it in pictures. I'm going to do both right now, okay? I prefer that you draw. So the p-value is the probability Something's happening. Hold on. Hmm. Okay, let me step back a moment. I told you that p hat is a statistic, and then I calculate z using p hat. So what do we call z as well? So this is a statistic because I calculated it from the sample. This is also a statistic because I used it calculating statistic. I used it, calculated it using numbers from the sample, right? So we're going to refer to that as the z statistic. So the probability of a z statistic as extreme or more extreme one second. I'm going to refer to it in general as a test statistic. Because sometimes I don't use z, so I'm going to call it a test statistic. This is a general statement. So here I'm calling it a z statistic. It's just I'll say in general test statistic. The probability of a test statistic as or more extreme of seeing a test statistic as extreme or more extreme given H naught is true. So what in the world am I talking about? I'm talking about thinking about the normal distribution that's really flat. And what I'm going to do is I'm going to plot this test statistic. Now, this is a Z distribution. This is with 0 in the middle. Where do I put negative 3.47? It's going to be over here. And rather than referring to the test statistic, I want the probability in the extreme, in the tail. Okay, that's what I want. So I'm converting it from a test statistic or a z-score into its probability because I'm going to compare it to a standard. So from problem to problem to problem, the results here, the results of the test statistic may vary, but I want to compare what I've got to a standard. I'm going to do that with the probabilities, and I'll show you what I mean. Okay, so I want you to find what is this probability here. So I want to see what's the chance of seeing a test statistic as extreme or more extreme. So what's the chance? How rare is it that what we saw? That's what I'm looking for. Okay, how rare, how bizarre is it? How extreme of a chance, that is, or how, yeah. How odd is it? What's the probability of seeing such a thing? Or even further away, okay, from the center. So you're going to go to the table, the Z table, because I use Z. think I have to use the same. And I look for that number. I look for -3 as a z-score, 0.47. It's over here, 0.0003, right? So I'm looking for 0.0003. That's what that is. Okay, so what does that mean? What percentage is 0.0003? It's 0.03%. So it's very small. Okay, but it's a very small chance of seeing what we saw, 20% when the assumption is 25%. It's too low. Okay, if we assume, because we've assumed that it should be 25, that's what that says. So what is too low? That's basically what I have to establish. In practice, we usually use a standard for concluding. This is the concluding step. We use a standard that the p-value should be less than a certain amount for us to reject our null hypothesis. So we found something strange. We found that in our sample, we got 20%. Now we assumed the sample was correctly drawn, okay? We assume that no one was lying to us. We make all the assumptions that the 20% is a good number. And then we have a problem because the 20% doesn't match. It's not even close to the 25% that we hypothesized. So we have to throw something out. Something's wrong. So what we're going to throw out is the assumption. Okay, we're going to say that something's wrong with the assumption. So that's what rejecting H naught means. So let me write this up. So p-value that we got was 0.03%. And as long as that's less than 5%, we reject the H naught. Now, where did the 5% come from? This is a convention that we use, that statisticians use. This is called the level of significance. If it's smaller than 5% chance and we saw it, we have a problem. We have to reject the hypothesis. The assumption was wrong. So in this case, we reject. And now we have to make a statement. What the heck? How do we conclude all of this? We say that there is sufficient evidence to suggest now you don't want to repeat, well, you could just repeat that we reject the null, but you want to say it in terms of the problem. There's sufficient evidence to suggest that, and now you can state the alternative, that less than 25% of people use vitamins. Okay, so that's the way to say it. You could also just simply say the test is significant. People who know statistics will know what you're talking about. What significance refers to the fact that we found something that it goes against the status quo. So statisticians, researchers, academics, they want to prove something new knowledge. They want to see, did we find something new? Have we broken away from what we've done in the past or what we've seen in the past. Yes, significant. We found something new. Less than 25% of people use vitamins. The test is significant. So this is the type of wording I want to see. You can put it in Spanish, the Spanish equivalent of that. That's fine with me. Just a couple of things to discuss. How did I know to go here? How did I know to do this? Where do I get the idea that I have to look in this extreme? I know that from, now I never use the alternative at all until that step, okay? This gets used in the p-value step. It tells me which extreme I'm going to look in, okay? So I'm going to use that. So I'm going to take that, and that gets used all the way down here. Okay. Otherwise, and then I state my, if I reject the null, I make a statement regarding the alternative. All right, so I don't know if you want to take a screenshot of that or you have it in the video. It's very small. I don't know if that's even going to be clear. But there it is, the whole problem worked out. And I believe I reviewed that in the videos as well. Any questions about hypothesis testing for a proportion? That's for the proportion. I went on the left side. You can do the same thing for the right side. Same idea, just have to use the correct table. Positive is going this way. Make sure you understand the symmetry of the table. We're going to do a couple more problems. But I'm going to do the left side and the to side because less than corresponds to this symbol. Greater than corresponds to this symbol, but not equals you recognize as this is not equal, or even if it says different from. Okay. Okay, hopefully this is just a review and you're not learning right now, but if you're learning right now, I hope you learned it. So those are the keywords you look for. So this one is greater than, this one is less than, and this one is not equal or different from. All right, let's go now. Let's just recap what I did. All right, so we've done hypothesis testing here. And we did it for the left side. What I'm going to do next, we're going to move to talk about testing hypothesis of the mean. And I'm going to do the right side there. And then I'll do a two-tailed there. So that's what we can do. Okay, so things are going to run really quick now because it's 10 o'clock. But that's basically the kind of problems you need to do, okay? So what is this? Test of hypothesis. This is known as inference on a mean. So this is inference on a population mean. And of course, mu is unknown. You don't know mu, you're trying to guess what mu is. But sigma is known. Now that's a little bit of a stretch. If I don't know something about the characteristics of a population mean, why should I know characteristic of the standard deviation? But that's where we begin, okay? So let's say we know sigma, then just like I built a confidence interval for the proportion up here, I'm going to do the same thing. The best point estimate, or what we call the unbiased estimator, of the true mean is the sample mean. And then there's the theory in Formula 3 that the, let me go back. Let's look at Formula 3 above. So from this formula here, this, I call it a formula because it's a formula sheet, but this is what we discussed last week about the distribution of the statistic X bar, and X bar comes from a distribution. One sample mean comes from a distribution of all the sample means that have a mean of the true population mean, but a standard deviation that's smaller. So we're going to use that here. And that's what that is. So that is the critical value, just like we picked one here. And the standard error is the standard deviation of X bar, which is sigma over root n. So it's the same format as this here. All right, so we can look at some problems like that. Then we have similarly the sample size estimation here, which is taking the margin of error, which is just this part. This is the plus and minus, the margin. This is going to be M. And then we isolate for N using algebra. We have this formula and we see the interrelationship between N and M. So let's go and try some of these, and then we'll get to the hypothesis testing. So I'm going to go to page 18. Page 18. So we have a sample of size 100 in Canada in hopes of estimating the true average height of women. So we want to try and estimate mu. We don't know it. The sample average is calculated to be, so this is information on X bar. This is the sample average. And we know that the standard deviation is 2. So we have this information. And then I asked you to calculate the different confidence intervals. Now I'm not going to do it. This is not hard. You have to use the formula each time. But we're going to talk about it. It says calculate the 95% confidence interval for the true mean of women's height. So what you have to do is take the formula, this one, and enter in X bar, which we were given 64, sigma we were given 2, and we were given 100. And then we were asked for a 95% confidence interval. So from the beginning of the class, I asked you to know about 95% confidence interval, the Z star critical value is in 1.96. Okay, so you get comfortable with that. So let's put all that together. You put that together, this simplified, I'm just doing step by step. And this is your margin here. And you can also make an interval. 64 is the point estimate. This is the margin of error. And this is your interval here. Okay. Now, the theory of the confidence interval, I told you last class, I would clarify or mention it again because it's in the videos. But the confidence interval concept is from the idea that we have X bar that is from the mean, the sample mean we got is from a distribution of sample means that are normally distributed, right? So if I have one sample from that one sample, so this is like sample A, simple random sample A, I can calculate the sample mean of A, and I could also calculate the confidence interval for that sample. I could get another sample, sample B, and take all the values and calculate its sample mean. So this sounds familiar because I was talking about all possible samples before. And we can calculate a different, this could be different, could be the same confidence interval. Okay, so these are the results. These are all like the statistics from the samples. And the ... indicates all possible samples. So you can imagine if you have a large population, you can have a lot of all possible samples, right? So statisticians built this theory with the idea that you don't have to get all of them. You're just going to get one because the theory says that let's imagine that we create an interval just like I did on the page that we looked at. So let's say the mean on, let's say this is the number line here. And let's say our true mean is like here. All right. So let's say we get all these values. We build a confidence interval. So this is my interval. They all have to be the same width. So this is my interval for that first result. This is the first sample. So this is my confidence interval for A. And I just touched the mean for this confidence interval. And I have to have a confidence interval of the same length. So I'm just going to copy it. But it might be like that. All right. And there's going to be others. And it might be like this. And there's going to be so the theory says that of all these confidence intervals that I could make from all possible samples, if they are a 95% confidence set of confidence intervals, ,95% of the 95% confidence intervals will actually have mu inside of it. That's what it's all about. Okay, so 5% of them won't. So that's your risk when you're using a 95% confidence interval. 5% of them will not have the true mean. So what you're trying to do, you don't know the true mean. You're trying to estimate it. We're using this theory to back us. And there's still a chance that we might not have caught it, but that's what we do. Maybe you can make a larger confidence interval, but the larger you go, the less precise you are, and it's meaningless. Like again, if you're making a confidence intervals for women's heights, before you even start the exercise or the study, you know that women heights are between like 3 feet and 6 or 7 feet, right? There's rarely you've ever seen women smaller than 3 feet, and like very rarely, or taller than 7.5 feet. You can say 7.5. So we want to be more precise. If we end up spending millions of dollars to do such a study, and we have a really large interval to hope to catch our mean, we didn't have to spend the money because we already knew that, right? We already knew that it was somewhere between 3 feet and 7.5 feet. You want it to be more precise. All right, so that's what a confidence interval is. There's several problems that test your understanding of confidence intervals. They are in English in the homework. I know there's some practice assignments that are in Spanish. Let me know if you're having any difficulty with that. On the test, if you have any difficulty understanding, just let me know. Okay, so the other thing I want to mention here is for the first one, I ask you to calculate a 95% confidence interval for the true mean of women's heights. But in B, I ask you to calculate the confidence interval that would be accurate 19 times out of 20. 19 times out of 20 is another way of talking about a 95% confidence interval. They're the same thing. Okay, so A and B are the same question. All right. And then 99.7% and 99%, these are different. This one will be a little bit bigger. You'll see that the Z star is a little bit bigger. And the 99% will be somewhere in between those two. So these values you get off your T table at the very bottom. So I don't want to calculate those because that's for you to practice if you haven't already. Have a look at those. I calculate them all on this page. And you can get the Z stars from, with 3 decimal places from the, well, I said the Z table from the T table. The bottom of the T table to get 3 decimal places. So when you see 3 decimal places, like when you're solving problems, it's just like a hint that you're supposed to be looking at the T table at the very bottom. So 99.7. Oh, no, we can't do that one from the T table. Sorry. That's right, because it is 9. Okay, let's go to the, that's why I had Z. Let's talk about this. Changing it. So this one, 99.7, is the standard one that we use in our, in talking about the normal distribution. But it's not here. There's 99.5, the 99.8, 99.7 is in between, so we don't find it here. So how did I get that result for Z? I created, if I want 99.7, I have to think about, if it's 99.7 in the middle, then it's, so this is the one that we know from learning about the normal distribution. However, that's only to 1 decimal place. So to be precise, using our tables or Excel, I must get the result on Excel. Or I think I estimate it. Yeah, that's what I do. Okay, so then this must be 0.0015 here. So looking for that number, I have 2 alternatives inside the table. Two alternatives inside the table, I see that it's between negative 2.96 and negative 2.97, right? So this is negative 2.96 and negative 2.97. So in that case, using the Z table, I don't know what I just did. Sorry, I didn't mean to do that. That's not right. So it's between negative 2.96 and negative 2.97. So you want to be between those two. So the thing that I taught you to do is go halfway. So it's negative 2.965 is equal to negative Z star. So the positive is 2.965. All right, so if it's not in the T-table, you have to compute it yourself, or you can use Excel, and I taught you how to do that. Hopefully you remember um, to find it. Okay, so if it's not in the T-table, you have to get it yourself. Any questions about that? You remember, so most of the stuff is just using things that you know, all right? Nothing new. Using techniques you've learned. Back to what I was talking about, 18. All right, so that's for confidence intervals. It wasn't 18, was it? Right. Okay, 21. So this is from the Z table, this number that I got. All right. So what we've discussed, and I hope you had a chance to practice it, but if you didn't, you're going to do it this weekend, is we've discussed applying, sorry, this is not where I want to be. Let's go back to 21. I have my formula sheet in a different document. All right, so we've talked about that. Next step, next column, sample size estimation. This formula is derived by isolating for n in the margin of error part of the formula. So to apply this, again, you just plop in numbers, but understanding the relationship between this. This looks like this formula, but remember, this one is, the one above is for proportion. This one is for means. So you should get used to seeing questions about the mean, like measurements and or ages or so things, variables that we've calculated for the mean as opposed to the proportion. So for example, I believe I continue with the same example here. And I ask you to estimate, using the same data, estimate the 99.7% confidence interval with a margin of error of m equals 1. We talked about the 99.7% confidence interval, and the Z star that we got was 2.965. Note, when we first learned about normal distribution, 99.7% correspond to 3, right? And again, that's for one decimal place rounding, like it's about 3, but because 2.965 rounds up to 3 standard deviations, but we're much more precise here, right? We're holding our decimal places, being much more precise. So to do this for 99.7% confidence interval with an m equals to 1, then I'm going to do the same thing, but with an m equals to 2. What's the difference between A and B? Which one will be bigger? Which one will estimate a larger sample size, A or B? A will estimate a larger sample size because you want more precision, right? The relationship is inverse. The more precision, the greater the sample size. So this is smaller, then the n has to be bigger. Very good. So what about the B and C? We want a 99.7. No, I'll do A and C. Sorry. So between A and C, same margin of error, but different confidence interval. Which one requires a larger sample size? A or C? Larger sample size. Let me erase this so it doesn't confuse you. A or C? Same concept. Which one requires more precision, A or C? So the M's going to be the same. So you want to be, in this case, your M is going to be the same, but you want more precision. You want, so you can even just see it here. This is going to be bigger. 99.7% confidence is wider. So the Z's have to be larger to do that. So A, right, is going to have a larger sample size. Uh-oh, some of you guys got that wrong. So Z star, let's look. Let's see. Right? So here are the results. A has a larger sample size than C. You guys get it? So that's because it's not the inverse, it's on the top. That's how you know. So a larger confidence interval means a wider confidence interval means a higher Z, right? Because the more spread out it is, the Z's are you guys good with that? Or you guys got it wrong in the chat? Are you okay? So you can make these calculations, that's fine. But I really want the interpretation. It's much more important to me that you understand, not just making calculations. So for instance, for the first one, when you punch everything in, you get 35.16. Should it be 35 or 36? From the discussion at the beginning of the class and the end of last class, we have to round all the way up to 36 to maintain our margin of 1. If we go down, we're going to lose precision. Higher sample size to maintain our precision of M equals 1. Okay, no, I know. I was confusing even when I was saying, I'm like, oh, they're gonna screw this up. Yes. But it's because they're not inverse. They're both on the top. The Z star is on the top there. Okay, good. Good. So here I just go through some of the discussion about the variables and the impact of the variables, but you have these examples to look at. All right, let's do the hypothesis testing, and we're going to do the testing of hypothesis doing the right tail because we did the left already. Then we're going to go to the T. I know I make things look easier when I'm around, but hopefully you can look back at these videos to get things to click while you finish your exam. All right, so let's try, like I said, let's do a problem of hypothesis testing that is a right tail problem. Or maybe we can do a difference problem. As I have a difference one. Let's talk about CEO compensation. Okay, I'm going to do the problem on page 28. No, I think that's a less than problem as well. Hold on. That is, yeah, no, not that one. Okay, I guess I'm stuck. Okay, I'm going to do the two-sided test now. Let's do that, and then we'll do the right side for the t-distribution. Okay, let's look at this one. So on page 22. Okay, on page 22. Oh, sorry, I got to share. Okay, so starting from here. Is an executive's blood pressure different from the population of males? So male executives. So think about male executives. Maybe you think they're more stressed out, or they have less, or they're in poorer health because of the stress. They have higher blood pressure. Okay, so this is a suspicion. In general, though, let's say we have no evidence to suggest there's any difference. We're going to begin with the status quo that executives, male executives, should have the same blood pressure on average as the average male and around the same age. So if we look at the National Center for Health Statistic reports, systolic blood pressure for males between 35 and 44 is between, it has a mean of 128 and a standard deviation of 15. So this is the information that's given. This is the status quo. Mu equals 128 and standard deviation, sigma, is 15. So we're going to say this is the status quo for males. And we have no prior evidence to suggest that male executives are any different. So we're going to use that. So that's our null hypothesis. The question is, so as I set up before, just like we talked about, it always looks like this. It's going to be, you put the colons here, and then the parameter you're testing there. So we used P before, now I'm going to use mu, and I have to still put an equal sign, and whatever number I put in the top, I also put in the bottom. So I already figured out the status quo. Whoa, that's a big circle. I already figured out the status quo. It's 128. So I'm going to use that for males executives too. And since I put it there, I have to put it there. And all I have to figure out here, next step, is to figure out, is this greater, less, or not equals? What do we want to sort out? The question was, is an executive's blood pressure different from the population of males? It just said the word different. It didn't say higher. It didn't say lower. It just says different. So which one do I use? Exactly. Not equal. So I'm going to use that one. Okay, so that is the key word. Another thing they could say is changed, but it doesn't say higher or lower. You can just say change. It changed. So with that as our null hypothesis, we're going to begin the problem. I'm going to set it up. I'm going to carry this. We're going to do the 5 steps. Now, you don't always have to do the 5 steps. Sometimes I ask for part of it, but you have to know how to do all 5 steps. So the last part of the exam where you get to choose problems, there's going to be problems in there. If you saw the mock, there's problems in there, and you will be asked to do all 5 steps. You need to do all 5 steps. You need to know how. But in the multiple choice problems, you don't necessarily have to do all 5 steps. So that's the null hypothesis and the alternative. So the next step to spell see is that we assume. We can't do anything unless we make an assumption. So we're going to assume that H naught is true because we don't know. Mu is unknown, but sigma is known. So we're going to assume H naught is true. And as a result, since H naught is true, executive blood pressure was like that, 128/15, in a sample of, how many did we take? I have to go back. We're going to take a sample of 72 and create the distribution of the sample mean. So we're going to calculate one sample mean from one sample, but it comes from a distribution of samples that are, notice it was normal to begin with, right? So it's from a distribution of samples that are also normal. Let me fix that. With the same mean, but a standard deviation that's smaller, sigma over root n. So 15 over square root of 72 gives you a value here of, I have to steal it from here, 1.77, I think. Is that correct? So what we've done is assume that mu is equal to mu0 of 128. That's our assumption. And out of there, everything falls out of there. Okay, so if I can do that, then I expect that the sample mean has this distribution. Questions? Next step, we're going to assess the evidence. What's the evidence? Well, we took a sample of 72, and we are told in the problem that the sample mean of the 72 is 126.07. Okay, let's take a step back and stare at it like we did the last problem that we did, the hypothesis problem. Is that different? Is this 126.07 different from 128 we hypothesized? I mean, if you've looked at the notes already, you know the answer, but just looking at them. So if somebody borrowed money from you for $128 and they come back and they give you 126.07, are you going to be so mad that they didn't give you, the extra $2? You're not going to be so mad. If they're a good friend or your little sister, you don't care, right? That's all they give you back. So they're not that different, but we need to assess it in terms of this very small standard deviation. We have to verify. We're not sure. It feels like it's not that big of a deal, but let's see. Assess the evidence. So we're going to take, we're going to calculate a Z statistic from our statistic. We're going to take X bar that we got. We're going to minus its mean, and we're going to divide by the standard error, standard deviation. So we get those from here. So X bar was 126.07. We subtract 128 and we divide by 1.77. What do we get? Again, it's a negative. $126.07 minus 128 equals divided by 1.77 negative. So now what do we say? Negative 1.09. We have more support for the fact that it's not a big deal. It's not much of a difference. Okay. In fact, in terms of our 3 standard deviations as a standard for an outlier, this is not an outlier. Okay, so we already know that we're not going to reject the null, but we have to go through the step to calculate. What do we calculate? We convert that Z statistic or test statistic. We convert it into a p-value. So that's the next step, p. The p-value, again, just for your sake, p-value is the probability of seeing a test statistic as extreme or more extreme given H naught is true. So we draw a picture. That's what it says. It's telling us draw a picture, and put, it's like your Z distribution. I don't know. Not doing a great job right now. Okay. And I'm going to plot the thing I calculated. I calculated this. So I'm going to plot it. It's going to be like here. And because, so remember, in the P step, I have to go back to this in the P step. Now I'm going to use that symbol. I have to, because it's not equals, I have to test if it's lower or higher. Okay, so I'm going to draw that as well, but on the other side as a positive. So that's when it's not equals. I got to go on both sides and I draw like this. Now, if the result ended up a positive, I would have to go to the other side and draw it as a negative on this side. Okay, so that's what that tells me to do. And then I look for the probability. That's all you have to do. Get the probability. All you have to do is one of them because of the symmetry. We know it's the same on this other side, on the right side. So let's look that up in the table. We're on the Z table, don't forget. Glass. And I'm looking up negative 1.09, right? Be careful with this, with the, decimal places. Negative 1.09 is all the way over here. Did I miss it? Negative 1.09 there. 1397. 1397. Now what do I do? So this is 1397, and this is also 1397, and together they make the p-value. So the p-value is actually equal to 2 times 0.1397, and it represents the probability of seeing 126.07 when it really should be 128. The probability is quite high, okay? It's quite high compared to the standard 5% that we usually use. So 2 times that ends up being what? 27.
Excuse me, Professor.
Yes.
On the table, it should be 0.1379.
Oh, I did it backwards? Okay.
Yeah.
It's okay. Thank you.
You're welcome.
I'll put it backwards. That happens. My eyes are blurry right now. I'm gonna grab my glasses too. Thank you. 7.9. No, 9. What did you say?
7.9.
7.9. Okay, so times it by 2. Okay, so it's 27.58%. %. All right, so I mean it's not a lot, like 30% is it's not high, like it's not a good grade, 30%, 27.58, but in terms of our standard in statistics, it's pretty high. Because for every question, notice I'm going to write the same thing that I did before as the concluding step. P-value less than or equal to alpha means reject H naught, but our p-value 27.58 is not less than 5% that we use. Sorry, 5%. I'm going to write it as a percentage. Sometimes I write it as a decimal, sometimes as a percent. Let me put it percent here as well. Let me write it again. It looks messy. Hold on. 27.58% is not less than or equal to 5%. So we write that we fail to reject the null hypothesis. Okay, so this is the formal way of writing what we already knew all the way up here. That is not that different. It's not 3 standard deviations away. It's not an outlier result. It's quite regular. So we fail to reject is what we write. We notice that we always write this, no matter if it's a left-tailed test, a right-tailed test, or a two-tailed test, or we say, that's to speak about the sign, the alternative hypothesis. If we're checking if it's less, it's greater, or not equals, it doesn't matter. This is always the rule, and we usually use alpha of 5%. We allow the chance to be 5%, but not more than that. So we fail to reject. Now we write it in words. We say the test, first of all, we can say the test is not significant. And you can summarize it in a way that's more, for publication, or you want to report this, you just say there's no evidence that male executives have a different blood pressure than other males. That's how you could say it.
Professor, so what we are saying here is that we bet that it will be different, so not equal. But since we got the 27%, that's why we are rejecting.
We're failing to reject. So we didn't find evidence. We didn't find anything special or new.
Okay.
Yeah, because it's not strange. It has to be smaller than 5, but it's not strange. We got 30%. It was, the chance was 30% in terms of statistics and in terms of hypothesis testing methods. That's acceptable. So there is insufficient evidence that male executive blood pressure differs from other males. I hope you can read that. Do you need me to write it? I'm writing. I'm not sure if you can read the cursiveness. It's just faster. It says there is insufficient evidence that male executive blood pressure differs from other males. So this is a moment I want to say that usually this is a standard, right? Tests will be done with 5% level of significance, and they're going to be two-sided. That's usually what you see, looking for difference, because if you reject a two-sided test, this is much more strict than a one-sided test. All right, because you have less area. So in general, so if this is our critical value, right? C star. And for 5%, it's negative 1.96. We discussed that, right? This is 1.96. So this is known as the reject region. And because I'm 95%, I'm putting 95% in the middle, I left 2.5% on each side. Notice it sums to 5%. That's why in total, I have to total because I have to compare to 5. So I'm comparing both sides. Everybody okay with that so far? But in a one-sided test, I still use the 5%. So if I rejected here on a one-side test, let's say I did it on this side. Make this smaller. So I just want to see if it's greater. I have to have in this whole thing 5%. Now, do you see if I rejected the two-sided test, I'm going to necessarily reject it for the one-side test. It falls inside. Okay, so usually the practice is just do the two-sided test. If you reject, then you're saying it's different, and then all you have to do is see the sign to know if it's lower or higher. That's sort of what's done. Now, I'm not going to test you on that, but I just want you to see this is why you'll see, a lot of two-sided tests get done, because it's kind of like killing two birds at once with one stone. Is that you already see that it's very strict. If you reject here, then it's gonna fall in here for sure. So it's going to be rejected on the one-sided test, whether it's on that side or the other side. However, if you fail to reject, and this is why you have the other test, if you fail to reject, it's going to be out here somewhere. And then you want to just double check if maybe it's still higher or lower. You might have to do the one-sided test anyway to see if it's in here. But in this case, if you reject, automatically you know that it's going to reject the one-side test. All right. Like I won't test you on that, but just see that there's a connection between these in that way. So, okay, let's go on to, okay, any questions? Because I know I feel like I'm rushing, and I hope I'm just reviewing and helping you synthesize all of this. But that is the hypothesis test that's two-sided, and it works the same for the P as it does for the mu. Okay, they use the same for the proportion as for the mu. The only difference in the steps is that you're using different calculations to get the mean and standard deviation, but always refer back to your formulas to remember what you're doing. It's very important that you get this first hypothesis step right. Okay, the next thing I want to do is go into the t-test and when the heck we use that, and talk about the t-table a little bit. Any questions about this? I'm going to make this smaller. It's just so big. I haven't mastered controlling the size of the pen. Okay. Okay. Questions? No questions? All right. Let's look at back there. Okay, let's talk a little bit. So I do have these graphs. I hope they turned out. Some of them got distorted, but this is the idea here. Fail to reject. I don't expect you to draw this. Just keep it simple. At this point, you have a lot in your mind. Okay, I'm going to go to the t-test. Okay, let me clean up a little bit here. I really like this example. Okay, let's start with talking about it. Okay, so um, okay, so to summarize, this was what we just did. We standardized that, we assessed the evidence. We standardized the result from the sample using the theory from number 3 that its mean would be the hypothesized mean, and standard deviation or standard error could be calculated using sigma divided by root n, and we put it here. It looks a little different, but that's all it is. And so that's what we did. All right, so we are on the last row. And what we're doing here is inference on the population mean mu. Obviously, mu is unknown. But also sigma is unknown. So this is the most realistic situation when you conduct a study about a population you don't know. You don't have information on the mean, and you obviously would not have the information on the standard deviation. You could make, if you made some guesses and you thought they were pretty good about the standard deviation, or you, or you wanted to look at, different standard deviations and see how it affects the confidence interval, or you wanted to run all of this with some hypothesized standard deviation, you could do number 5, right? But in reality, you probably don't know it. If you don't know it, the best or the unbiased estimator of the standard deviation is S, the sample standard deviation. So this is the sample result, and this is also a sample result, and there's a price to pay for that. We don't get to use the Z distribution anymore. We have to use the T distribution. And who wants me to talk about the T table? Anybody want me to discuss the T table? Or did you follow that in the videos? Or I can spend a little time on the T table if you want. Put it in the chat. Otherwise, I'm going to just jump in to using it. Okay, let's explain a bit. All right. Okay, we're going to talk about the T table, how to use it, how it's similar, how it's different. I think I have it here. I have my drawings on the other one there. Okay. Okay. This is the T table, and I did this explanation last time, and I said that as the sample size, so it depends on the sample size, but we convert that into what's called the degrees of freedom, which we learned about back when we talked about the sample standard deviation. As the degrees of freedom increase, as the sample size is given, degrees of freedom is equal to n minus 1, just one less the n. So as n increases the sample size, the larger your sample size, obviously the larger degrees of freedom. The tails flatten. Okay, so it becomes, that's the right word, but it becomes more peaked. And the more peakness, so it goes from being really, I'm going to rewrite that because I don't like what that says. I'm going to say the tails thin out, okay? And the distribution is more peaked. So as it goes, it becomes more peaked, and in its limit, it looks like the standard normal. Okay, so it's centered at 0. It's really flat at first, but then it narrows. And that's important because at the very extreme, you have as the table, as you go down the table, those are sample sizes increasing. Let me start at the top. So the sample size, this is a sample size of 2. So degrees of freedom, 2 minus 1 is 1, and it increases all the way down. So if you have larger sample, after about 1,000, there's really no difference between the T and the Z. So I have the last row is just all Z. Okay. So you'll notice in studies that they'll use the T distribution a lot. But with large sample size, it doesn't really matter. They could be using just as well using the standard normal. All right. So I want to talk about this because on this table, you have just one row of values, 12 values. as opposed to in the standard normal table, you have hundreds of values. Okay, you just get 12. And they're only on the right side. They're all positive. But because of the symmetry, by this point, you should be comfortable understanding what it would be on the negative side. Okay, so I have a few examples in the notes practicing working with this. The focus is that this table is focused on you looking for the t-score or the t critical value inside the table as opposed to the margin. Okay, it's inverted from the z table. It's the other way around. The probabilities here are on the margin, and they're just the upper tail. Okay, you don't have a negative table and a positive table. And this is to facilitate all the different distributions that we'd have to use with the sample size changing. So I have a few problems, and I've extracted the data from here. And let's see. Oh, no, I didn't go that far. Hold on. It's over here. So I've taken the table here. Let's erase this. Draw. Also, you can get this out of Excel using T, just like you did Z. You can get these results out of Excel. So let's say I asked a question like, what is the probability that the T distribution is greater than 1.5? So this is like your T test statistic, and you want to know the tail probability for 1.5. You have to specify the N to do this, okay? So someone has to give that to you. So right away, once you know the N, draw something that looks like, the usual drawing. Oops. Oh my goodness. I have to put my hands. Okay, so this is going to be degrees of freedom 19 because sample size was 20. So I'm going to draw it right away like that, just to avoid forgetting, because you're going to see a lot of numbers in the course of doing exercises or your test. So you got to be clear. So I want to go to the 19th row. And on the 19th row, I look for the number 1.5. So this is like this opposite. So I go to the 19th row and I look for the number 1.5. That's going to be the critical value in there. Now it's not there. 1.5 is not there. But the best thing I can say is that it's between 1.328 and 1.729. That corresponds to these tail probabilities. So I can actually draw this on my crooked thing. Let me fix this. It's so crooked. So I'm gonna draw 1.328, and then 1.79 is here, 1.729. Like it works like the same as a number line, right? Gets bigger and bigger. And these correspond to a right side probability. You have to go here to see it. So it's 5% to 10%. You see, we're going to start with the smaller one. That's 5% on the left, on the right. And this corresponds to 10% on the right. And using the table, that's the best you can do. Now, solving the homework or doing my review exercises, you're going to be using the table results like that. But this is the best you can say that the result is between 5% and 10%. But if you wanted to get the number because it's bothering you, you can get it in Excel. I can try that. Excel wants to know, just like we needed, the degrees of freedom or the N, and it wants to know the critical value that you want. Excel should give you the left side, okay? Just like with the Z distribution, it gave you the left side. It gave you the percentiles. But let's see, let's verify because now I'm doubting myself. Let's get and you. So in Excel, here's my workbook. And I'm going to type equals to look for the formulas. And I'm going to put T. Which one do you think I should use? What do you think all these things mean? So T distribution will give you the result, probably the percentile. T distribution, two tails, right tail. T inverse would be the inverse test. This is the inverse two tails. So let's just, all we want to do is use the T distribution. Let's see what it says. So you got to put in the value X. So we have 1.5. And the degrees of freedom of 19. So what do we get if we put that in? And we say cumulative. We want to add, we want, you want the left side, or you want the, the area to the left. If I put 1.5, I get a very large number, right? Because it's saying, it's going from the left of 1.5, but what number should I put here to get it out of Excel? To get the left. Sorry, to get the tail. If I put negative 1.5, it gives me, so let me copy that so you can see what I just did. If you guys. Okay, so that's what I wrote. And I wrote the negative because the Excel works always with the left side, the left tail. But I want the right tail. I want to know the upper tail. So I'm just going to use the idea of symmetry and put negative 1.5, and that will give me the answer between 5 and 10%. You see? So you guys don't have to use Excel. I'm just showing you there's an option there. Do you want to play with that? The table should be fine. Any questions? Just remember, Excel will always give you the left side. So when you're using when you're so it got 90, it gave 92 because it was giving the left side of this, right? It was giving the left side of 1.5, which would have been all of this that way. That's not what you want. So you're going to use the negative so that it's giving you this side here. That's what Excel does. All right. Is that okay? So that's how you use the table. Notice if I go left of 1.5, the answer is going to be the complement. So not between 5 and 10, but between 90 and 95 if you're going to go this way. So in this case, that would be the right answer, 90 to 95. And I did a bunch here. You can take a screenshot or you can look at this. I solved all these. The solutions are all there as well, but these are the drawings that go on along with the explanation. The main thing is, let's start here on, I'll do these two here. So let's say instead we want to find the critical value. Okay, want to find T. Where you're told that the upper tail, so that's what that says, is 0.005 or 0.5%. With a n of 17, we have to look at the 16th row. So we go to the 16th row. Let me erase this. We'll just do this together. And you want to know where, it's very small, 0.005. You want to know what is T for that value. So it's the backwards or the inverse problem. This is very easy in Excel to get. It's got to be careful because Excel gives you the left side results. So let's go to the table and look for 0.005 on the row 16. So if we go to the row 16 and we look for 0.005, this is our value here. It's very easy. 2.921. So it's actually using the probabilities and getting the t-score. It's easier on the t-table than it is on the z-table. It's very easy. So this means that you have to be at 2.921 standard deviations from the mean. Let's do this one together. I'm going to clear it. Okay, so find the critical value where n is 10 and the area to the left is small. So let's draw it so we know what to do. So I'm going to draw this and I'm going to put 0 here to remember that. And there's a small area here. I want to find T. It's going to have to be negative, correct? And we want it for T9. All right. So try that yourselves. You guys are still here and you're watching me. I guess I'm going to just keep going. If you want to go and study, you can go study. If you want to stick around, just stick around. I'm going to do a couple more problems after this one. And then I'll stay back, or Aleximar or someone asked me a question. I can look at that too. Can't remember if it was Aleximar or Damaris. But anyway, it's in the chat. Okay. All right. Did you do it? So we're going to go to the 9th row. And we're going to look for that number 0.005 in the tail. So it is 3.169, sorry, 3.250. So it's 3.250, but I have to know that it's a negative because it's on the left side. So it's really important to draw this. You're going to get confused otherwise. Let me clean this up. All right. So, and again, there's some other problems. I have them described and I just showed you the graphs. So let's look at, I want to do a right-tailed, right? I want to do a right-tailed test. Okay, let's do this one. I'm going to do 2 and 1 here. Okay, so this is a right-tailed test. We want to test, so it's coming full circle. From the beginning of the course, we talked about experiments and we discussed how to set up a good experiment. And then we learned all this material about what to expect given certain parameters or shapes of distributions for different characteristics. We talked about matched pairs design when we talked about experiments. And now we're going to actually we're going to learn here, or hopefully you looked at this already, how you assess whether things have improved after you conducted a matched pairs design. So here's an agricultural example where we have plotted, let's just imagine that we did this properly. We've plotted some plants, some tomato plants, and we say that the yield, so their production, is known to be normally distributed. And we want to know whether this new fertilizer that we use improves yield from the old fertilizer. So we only have 4 observations here. Everything is nicer with more observations, but every observation costs money. So we just have 4 here. We don't have any other information except that we know that the yield is normally distributed, and that helps us because we can appeal to the properties of the t distribution to do this, because we don't have any information on the new thing that is the difference. So this is like a new distribution, this idea of difference. What am I doing here? So here is my old data with the old fertilizer. Here's my new data with the new fertilizer. And I want to see if there's been an improvement. To test for an improvement, I am able to subtract the old fertilizer results from the new ones and create like a new data set. So this is my new data set. So doing this kind of matched pairs, this is called a matched pairs or paired t-test. But it's just like if I didn't have two sets of data, I would just do this. So the only thing I'm adding here is that I subtracted this to create this data set. And from here on, this is what I do. They're paired in the sense that I set it up so all the conditions were identical, except the fact that I used a new fertilizer. So the same kind of seed, the same kind of soil, the same kind of environmental conditions makes these paired results. Okay, so the paired result analysis is the same. Once you subtract them, is the same as doing it with a one data set t-test. All right, so I'm going to test that there's been an improvement. How do I set up the null hypothesis for that? So we're going to start there, our first step. So this is a test. In my notes, I always have like a D here, like the mean difference. You don't have to put that. Basically, I want to study this data set, okay? And that's all that matters. So I want to check for the difference to be what against what, and whatever number I put at the top, I have to also put at the bottom. So first question, what number should I use to test for an improvement? The keyword is an improvement. That's the terminology there. Remember, I always have to put an equal sign here. Or what number should I put first, Brian? So what number do you expect here if there's an improvement? Nope.
It needs to be greater than the mean of the old data set, no?
Nope, you don't use the data set results. You use the status quo. You use the fact that what? I don't want to give it all away. There you go. So if it's improved, it should be better than zero. This difference should be better than zero. Some of them are negative though, see? But they should be greater than zero. Against this is zero, and this is greater than zero. So that is what you're testing. Does that make sense? So when you do a paired test, you have to think about the difference, what you expect the difference to be. Usually it's going to be zero, but sometimes, if you want the difference to be more than $10,000 difference and you're testing, increase in sales or something, you could put that here, but depends on the problem. So if you're looking for an improvement, it just has to be bigger than zero against equals zero, that it didn't change, because this would be the status quo. It didn't change if it's zero, right? On average, didn't change. Questions about that? Okay, so, all right, so let's conduct the steps of HAPC to solve this. Let me see if I can just move this over. So we have the new data set. I'm gonna put this at the top. All right, so that was the H step. Now we're gonna take assume. Now when I do a t-test, I put these together. Assume and assess just go together. And I say that remember, this is H not here, that I've assumed it's zero. And what I'm going to do is I'm going to see that I'm going to convert this to a t-test. I'm going to take 0 minus the mean, divide by the standard error. No, I did that wrong. Did that backwards, sorry. I'm going to take the result of the sample, I'm going to assess with the mean and divide by the standard error. Okay. So what is the mean? In this sample, we have to calculate the mean. So take out your calculators and get the mean and the standard deviation very quickly, efficiently. As I told you or showed you, you put your calculator into stat mode, clear the information, entering in 0.2 negative, enter down. You skip through the y's, right? You just enter the x variable. 0.5, enter, and down, down. 0.9, enter, down, down. And 0.5 negative, enter, down, down. Once you have the data, you ask for the results, statistics, and you scroll through and you get the mean. And you continue, and that's the sample standard deviation. Those are the results that you use. So those are my evidence. So I calculate that. So X bar is equal to 0 point, let's go back, 0.175, and S is equal to 0.6397. I held 4 decimal places. My data has 1 decimal place. Usually I hold 2 more, but I held 4 in this case. Oh no, I rounded it, okay, to 3. So I'm going to round that to 3.64. Okay, are you guys with me? So in this problem, I don't give you the mean or the standard deviation. I don't give you sigma. I give you just the data. You have to compute or create the difference data, realize that this is a matched pairs, that it's 0, and then conduct the calculation, computing the test statistic. The mean hypothesized mean is 0. The standard error is not sigma over root n. It's S because we don't have sigma. This is a study. We don't know the standard deviation of the differences, right? It's a new fertilizer. We don't know anything about it really. And differences from old fertilizers. That's why we're conducting the test. So we need to calculate this as a standard error. So that is going to be 0.64 divided by square root of, wow, just 4 observations. And what do you get for that? Right, 0.32. All right, so everybody okay with that, those steps so far, I hope? So what I had to do was create the new data set, calculate its mean, its standard deviation, and now I'm ready to apply or use them in conducting this test. All right, so I've already done H, A, and A. And we assume that this is standard, well, this is t-distributed with how many degrees of freedom? Always when we talk about t, we have to use T3, okay? Because n was 4, we have to use T3. Are you ready? Next step, p-value. Draw a picture. Which picture? T3. I mean, this is not an accurate drawing. Let me make it flatter. All right, so there's my T3. I can't use Z anymore. I have to use T. So with T3, I'm going to plot the T statistic. What is the T statistic? Did I get it yet? Oh, I didn't get it yet. So the T statistic or the test statistic is equal to X bar, which is 0.175 minus the mean, which is, remember, it's over here, 0, which is weird, but that's what it is. Feels just funny. That's so easy. And then divided by 0.32. And now you have the test statistic. What do you get? The table only has a few decimal places. I only think 3, so can round it. 547. Okay, so we're going to plot it here. So remember, for the p-value, we want the probability of seeing a test statistic as extreme or more extreme. So I plot it. That's all I do. Just take the number and put it on the graph of the T3, 0.547. And what I want to do is, again, I have to use that sign. I want to go greater. Define, so extreme is defined in the direction of the alternative hypothesis. That's what I want to test against. All right, so now what do? I have to go to the table, look on row 3 for that number, see if it's there. Let me pull up. Maybe I can get the table from over here. Can I get the table from over here? Okay, this is good enough. Okay, so I'm going to look. Let's make this bigger. So T3, what do I see on this table? It's 0.547 there. It's not there, but what do I know? I know the closest one is this one, 0.765. I'm going to draw it, okay? I'm going to draw it. on the graph, and then this is 0.25% on the right. So 0.765 oh no, I missed it. Better do this way. I should have taken note of this exercise. So notice so 0.765 is here, right? I mean, yeah, 0.765 was here, and this was 25% on the right. Let me go back. This is page 52. I need to take this with me. You know, I'll just go out. I'll go out here and get it. Oh, I don't think I can. I think it's here. It's actually closer if I get it here. Oh yeah, so I did it wrong. I don't know what happened just now. Sorry. What was I thinking? Not thinking. That's not there. It has to be further out. Okay, let me draw that again. Or let me go backwards. Let's see if I can go backwards. No, I can't. So yeah, I drew that backwards. So let's just switch those. All right, so I have my value that I put down as 0.547. I apologize, 0.547. And the one on the table is 0.765. Which is over here. Let's go look at the table. On the third row, and the first one we have is 765, right? And of course, that's further down on the number line. I just confused myself. So this is 25%. And that's the last one on the chart. So it's like, oh, well, what do I do with something not on the chart? Well, what do you want to say about it? What's the area to the right of 0.547 on the T3? It's going to be greater than 25, but it's less than 50, right? Because I don't have any other values, but I know that it's not a negative. So if this is 0, this is 50%. So basically, it's high. So we already, remember, we want a small probability, but this is high. So we're not going to reject here. We're going to fail to reject. So there's a few things to notice here. We do not feel comfortable or confident about the t-distribution. So we really need to rely on the table and know how to use the table well. When I got my t-stat, I didn't know what it really meant because on the z-table, 0.54 is small. It's a small difference. It's not that, that's not that different. Notice our mean here, 0.175. We would compare it to the 0. Is that different? Is it not different? We're not confident, right? So we really got to be careful about our calculations to do this because we're not so familiar with the t's. There's so many of them, right? Depends on the sample size. So the test is the same. P-value less than or equal to alpha means reject. It's still the same. If it's a left test, a right test, a t test, a z test, doesn't matter. It's the same question for the concluding step. So let's fill this in. So the p-value we got was, we're going to say between 25 to 50%. We don't know how it is. It's probably closer to 25, but whatever. We'll leave it like that. And we want to see if that's smaller than 5%. What do you say to that? It is not. So we fail to reject. And we conclude that, well, you guys tell me. How do we conclude here? How do we conclude? Right. We have not found a difference, right? We have not found a difference. So there's no difference. Very good. We failed to reject. We retain the null hypothesis. So there's insufficient evidence of an improvement in yield. So the test is not significant. All right, so this is a matter of you feeling comfortable with the t-table. Go back and see if you can learn the t-table if you're having difficulty, or use Excel to get the value. But remember how that works. That also can be confusing because it gives you the left side. You would have to put in the negative version of this number to get the exact p-value. And remember, the highlight here is that doesn't matter if it's a t-test, doesn't matter if it's a paired t-test, doesn't matter if it's a z-test, doesn't matter if it's a right tail, left tail, difference test. It's always the same statement that we're assessing. Okay. All right. Any more questions? I am going to just say there's a couple more things, and then I'm going to do Aleximar's questions. So we focused on alpha of 5% because that's the standard. But if you want to be more strict, or you're told to be more strict, you have to require even a more rare, a more rare standard, not just 5% chance of seeing something that you see. You want it to be even smaller. So you want it to be like 1% or 0.1%. Okay, so the more conservative, the more strict you want to be about saying that something has changed, or that you have new, just new findings, or the status quo has been upset, right? The only way to do that is by going smaller in your level of significance. Okay, so let's see if I can look at Aleximar's questions. If people have to go, you obviously can go. I'm just going to put up the recording so you can have a look at it. You guys are all still here, hey? So let's do her questions. Let's see. Oh, there's one more thing. Yeah, one other thing I want to say about the formula sheet. Oh, and something about, I want to say something about the homework questions. and knowing when to do which approach. All right. So notice this is missing here. We have, this is the equivalent of the confidence interval that I did here for the others. Point estimate plus or minus critical value times standard error. And all I did was substitute sigma in the place of S. And because of that, I had to pay the price and use T star rather than Z star, which is something new. It's not hard. You just have to get used to it. And for the test of hypotheses or hypothesis, I use the same pattern, right? I take my evidence and I standardize it using the inferred value or the hypothesized value. But there's nothing here. Why is there nothing here? Does anybody know? Did you watch the videos? Do you remember? Why is there nothing here? Let's assume that there was. Let's put in, it should be like just like before, but with instead of sigma, I put S. Why is that not there? What is S? S is equal to the square root of 1 over n minus 1 xi minus x bar squared. Notice the problem is that n is still inside. We didn't isolate for n. Okay, so this is the problem, that we have not isolated n on one side. You could solve this, but not algebraically. You could do it with a computer, like in Excel, and try and balance the equations, you know, taking different values of n, like different sample sizes, and trying to, you know, this number would change and this number would change, and see if you can get them to equal. It's very confusing, but anyway, you could, but yeah, you're not going to be able to do that as simply as we did it here, just solving for or isolating n. Okay, so that's why it's not there. It's not there's no algebraic solution for it because n is still inside. We haven't isolated n perfectly. Okay, so what was the other thing? Okay, Eliximar's question. Oh yeah, I wanted to show you the homework. I wanted to talk about the homework a little. Let me show you on the platform. Okay, so here is the platform. And I have to change it to my view. It got kicked out. What's happening? Oh, sorry. There. So the biggest problem is knowing when to do what, because you have a lot of formulas and things. If you follow in the homework, there are almost 100 problems in here. Some of them don't apply because I stopped the examination with the material on paired t-test. I have extra material in the notes, but it's just for completeness. I'm not going to test you on it. Okay, very good, Eliximar. Thank you. Okay, so when you're reading these problems, let's read this together, okay? Maybe you've done it. If you haven't, let's look at this together. And you're going to tell me whether I use the formulas in 5 or the formulas in 6, okay? A gas utility company wishes to know how much time is needed for the service person to handle a service call. A random sample of 16 gave an average time of 62.2 minutes with a standard deviation of 5 minutes. The 95% confidence interval for the mean service call time is. So should I be using the formulas in, let me go to get the formulas. Should I be using 4, 5, or 6 for the confidence interval? Which formula should I use? 4, 5, or 6? For this problem? 4, 5, or 6? Put it in the chat. Come on, come on, come on. 4, 5, or 6. Okay, keep going. Tamaris. 4, 5, or 6. Come on, come on. You're 20 there. I expect to see at least 10. Keep going. This is a very important exercise to be able to identify which is the appropriate formula. All right, so all of you are wrong, except for Alejandro. Damari says standard deviation known. Okay, so this is all about reading. Okay, so we read here, and do not assume this is the population standard deviation. You cannot assume that. It doesn't say it. It actually says a random sample of 16 gave. These are sample results. This is the sample mean, and this is the sample standard deviation. Okay, so don't feel bad. You saw that most people, everybody except for Alejandro got it wrong. Okay, so you have to use the T. In fact, most of these exercises are using T. So if you're getting them wrong, it's because you used the wrong one. All right, so be careful. If you have questions about the exercises while you're doing the test, you can ask me about the exercises. You can't ask me to solve problems on the test, but if you're having a problem, you don't know, Professor, why did I get this wrong? You know, if you're still studying, just ask me and I'll point you in the right direction. But please don't depend on me because can't ask me for everyone, but you shouldn't. But basically, so that's right. Okay, let's read the next one. Let's read the next one together. Well, not that one. Let's read number 4. Okay, try that one. A cannery prints 16 ounces on the label of one of its products. The quality control supervisor selects 9 cans at random and weighs them. He or she finds that the average weight of the 9 cans is 15.7 ounces and the standard deviation of 9 cans is 0.5. There is no population standard deviation here. It's only sample data. This is more realistic, okay? In the end, that's what you get. You have to use the theory using the sample results. So the number 6 formulas are very important and used very often. Okay, so this one would also be that you have to use number 6. Okay, I'm going to give you one more without me giving you the answer. Let's see, because most of them are, like I said. Okay, what about number 7? Which formula would you use? Now you're going to use it in a different way because they give you the confidence coefficient, 99%. Okay, so that's confidence level. So they're giving you there the interval, and you have to find the sample size. So this is a margin. So which one do you use here? Which 4, 5, or 6? Which sample size estimation do you use? 4, 5, or 6? Second column. Four, 5, or 6? The blood pressure of adult males is normally distributed with with a standard deviation of 5 units. In order to estimate the mean blood pressure to within 2.5 units with a confidence. So this within is like the width, right? No, this is the margin, 2.5. This is the margin. So this will be your M. This is your Z star that you have to go find. 5 or 6. Damaris 5, Maria. Perfect. You guys took a little pause there, but yeah, this is 5 because you can't even do it for 6. So that's a giveaway. But you're not given, you're given the populations because they say normally distributed with standard deviation. So that is population information. So you have to distinguish what's the population information, what's the sample information to solve this. All right, let's try another one. Let's keep going. Be careful with this one because they tell you here. Well, anyway, what would you use here? 5 or 6? 4, 5, or 6? What would you use here? 4, 5, or 6? Four, 5, or 6? You know it's not 4 because it's about X bar. It's about the mean. So it can't be 4. Okay, so that's the first step is knowing if it's a mean or the proportion. But they give you X bar, so you know it's going to be 5 or 6. And okay, and they don't give you sigma anywhere. They don't talk about the population standard deviation. So it has to be 6. Be careful though, because they give you S square. You need S. You have to take the square root for that one. So be careful. Good, good, good. You're getting the hang of it. So that just let's just, skim through. So in fact, you spend a lot of time on modules 8, 7, and 8 and working with the proportion, but in fact, in this inference thing, it's mostly about the mean. There's just a few problems for proportion, and I put some extra problems online too for you to practice. Okay, let's see this one. What do we do here? 4, 5, or 6? So the first question, is it about the proportion or about the mean? And here in the first sentence, it says, concerned about the real average amount. So it's about the mean. Okay, next question, do you have the population standard deviation? Is the population standard deviation here? Exactly. There's no population standard deviation, so it's 6. Okay, so that's the thinking process. First, proportion or average. Second, If it's average, do you have the standard deviation? So it is 6. Okay, so that's the idea. So again, if you have trouble with any of the problems I've given you, you have questions about any of the problems I've given you, you can ask me, okay? That's fine, I don't mind. You just can't ask me to give you the answer on the test or anything. All right, let's see. Okay, let's do the chat problem. No, Eliximar, so that one, so you're okay with that then? You don't need that anymore? Question 6, my question. It's final exam 2, question 6, okay. Okay. Yeah, okay. Okay, so any more questions from you? You want me to do any more problems? You saw the mock final. If not, look at the mock final exam. And I've put the solutions. Oh no, I lost power. Lost power. I lost power. Are you there?
Yes, we are.
Yes.
Okay, I lost power for a second. Very good. All right. Oh, my picture doesn't work. Oh, whatever. Why doesn't it work? I lost power. I lost my camera. All right, so hopefully the recording continues. So, any other questions for me? There's going to be options on the test. You know your strengths, work with your strengths. You have all the material online. You can continue to study. Hopefully you can take a day off of work or something. Somebody can help you with work, or I don't know. You can find the time to do the test in the next 4 days. Did I say 4 days or is it 3 days? Saturday, Sunday, Sunday, Monday, Monday to Tuesday, 3 days. It's more than 3 days, but I have to submit the grades. Let me verify the date that I have to submit. See if I can give you any extra time. They did change some dates. Okay, último día. What is it? Okay, I have till the 15th. Will it help you if I give you to the 13th? If I change to the 13th? The deadline? Te ayuda.
That's until Thursday?
Yeah.
Okay.
Does it help?
Yes, it does. Yeah.
Okay. So yeah, because I need a day to put everything together and enter into the system. Let me make sure that I'm right about it. It says It does say 15. Yeah, that was always the day. Okay, so if you need any explanations about any of the material, just contact me. I can meet with you or direct you in some way, okay? So keep in touch.
So the test will be posted from what time today?
From 1 o'clock,
Okay, super. Thank you.
okay? Follow the directions like you did before, and it should be fine. You should have everything at your fingertips, so you're fortunate, and you have an little extra time, a couple more days. Okay? Okay, so have a good weekend. It was a pleasure meeting you. If you ask for evaluation, please submit the evaluation because otherwise just the very upset people submit evaluations and that's not good. So please, if you can offer your recommendations, any comments are appreciated. It was a pleasure teaching you and I hope to meet you or bump into you one day. Enjoy the rest of the program. I know this is just the start, so hopefully it was a good experience and you learned something about statistics that you can take with you. Okay. Sorry about my camera, whatever. I'm gonna have to work with that. What bad timing. Okay, have a good weekend. Have a good week. Keep in
you.
touch with any questions. Ciao.
Bye.
Professor, there in the mock exam, there was some questions in section A that said show your work. So that I just wanted to clarify. In the first section, would we have to show the work of all of the questions or just the ones that say show your work?
Oh,
Mm-hmm.
you should just show it. Unless it's like a question that's a word problem that you don't have to do any mathematic calculations. If you feel that it's iffy, make a justification or an assumption or say something because
Okay.
that can support you with part marks. Also, I want an extra
Okay,
day to be
thank you
able to
very much.
post the grades. You can see them before I post them to the registrar. Hopefully that will happen. Okay, Alejandro, thank you.
Where
for
can
the
we see
question.
that when it's
In the platform, if I put them in Moodle before I post them to the registrar, I put them in Moodle. You'll see them there. Because I have to update the
okay,
participation so you can see everything, participation, connect, everything together. I'll work on that.
okay, thank you.
Okay. All right, guys, ladies, gentlemen. Good luck. Keep studying.
Question for you.
Ciao.